Hello, welcome to the course Electronic System Design. Last few lectures we discussed about the KiCad software, and then we saw that we can create schematic in KiCad where we specify the connections between different components what we want to use. Then we saw that we can create PCB from this schematic directly. We can import into the KiCad and we can draw the PCB using various layers. And we also saw that when we use these components, it is not possible that all the components are available in KiCad software. So, there are two options. One is we can go to the manufacturer site. If there is already available footprint and symbol, we can download that, include it into KiCad, or the other option is we create it using the physical measurements of our component. Usually all these measurements come within the data sheet. When we buy the component, by that component number we can search on internet and we get these data sheets. In the data sheets we generally have the footprint dimensions. So, accordingly we can prepare those footprints and symbols, and we can use these custom symbols and footprints in our schematic and PCB. So, that is what we saw in the last few lectures. Today we are going to discuss how do we start a project right from the very scratch and we complete it using the KiCad software. So, we will have some hands-on experience on the KiCad software. We will open up the software, we will start designing that particular project and we will reach to the final goal, which is the PCB design for that particular system. And through 3D viewer we can also visually see that how our PCB, the final PCB will look something like that. So, today we are going to use any project. We will take from the very start, from the specification design for example, and then we will take it systematically, that what are the steps in between right from the specification to the final design. So, for today's exercise, let us take one example of an analog circuit using a standard OpAmp circuit, which is very widely used component in analog designs. So, today we are going to use a OpAmp circuit and try to make some project. So, the project we are targeting is such that, for example, we have 4 or 5 inputs coming in from various sensors or at various locations. We are getting these 4 signals and we want to add up these signals. So, for this kind of work we generally use a summing amplifier which is made by OpAmp, and we want to implement this summing amplifier. So, we have these 4 signals coming in. We want the output, which is a single output, which is nothing but the addition of all these 4 signals. So, these signals we can algebraically add it. For example, we just add it V1 plus V2 plus V3 plus V4, or we can have a weighted sum. For example, V1 should be as it is, V2 whatever is the voltage or the value, half I will add up into V1, V3 for example quarter of V3 only I will add up to get the output. So, V1 plus V2 upon 2 plus V3 upon 4, something like that. So, this kind of addition I want to perform on my analog signal. So, we have 4 analog signals. We want to use a summing amplifier using OpAmp and want to generate a output which gives me the sum of all these signals. So, this is the problem statement, and we want to create a PCB which is going to do that. So, we will have 4 inputs for these 4 signals and 1 output, which is the summing result of all these signals. Of course, apart from these 5 pins, we will have power and supply, power and ground pins to power up our PCB. So, this is the problem statement and we want to create the PCB for this problem statement. So, let us see how we proceed. So, first let us discuss what the summing amplifier look like and how does it operate. Then we will create the schematic and then we will go to the PCB design for this summing amplifier. So we discuss the summing amplifier. This summing amplifier is used to add signals generated by various sensors. So from the analog electronics course, we know that structure of summing amplifier looks something like this. We have a OpAmp, this has two terminals, negative and positive, and the output in summing amplifier we have one feedback resistance, and then we have, let's say, 4 signals we want to use, so we have 4 resistances. So these are 4 resistances. The circuit looks something like this. The positive terminal of op-amp is grounded and the negative terminal is connected to all these resistances. These are connected here. This signal is, let's say, V1, this is V2, this is V3, and this is V4. This resistance is in feedback. So this is how the circuit diagram look like, and we can name these resistances. Let's say this is R1, this is R2, R3, R4, R5, and this is our output pin. So if we see carefully here, the positive terminal of this op-amp is grounded here. It means this connection is at 0 volt, and we know that both the terminals of op-amp are virtually short circuited. It means whatever is the voltage here at positive terminal, that is going to be the voltage at this negative terminal. It will be induced here. So this terminal is going to be 0 volt. And if this is 0 volt, whatever voltage we are applying, let's say at V1, which is the signal coming in, there will be a current from this V1 to this node which is at 0 volt. So the current through V1 is given by, let's say, I1 equal to V1 minus 0 divided by R2. So this is V1 divided by R2. Similarly, I2 current from V2 will be V2 minus 0 divided by R3. So this will be V2 divided by R3 and so on. I3 will be V3 divided by R4 and I4 will be V4 divided by I5. So all these currents will be produced by these signals V1, V2, V3 coming in. This current, when flowing from V1 to 0, all these currents are approaching here this node which is at 0 volt. Now the input impedance of op-amp is very high, so current cannot go inside this op-amp. So there is no current flow in this direction. So all the currents whatever coming in here has to flow into this feedback resistance R1. So the current flowing into the R1 will be this I1 plus I2 plus I3 plus I4. Here the current will be, let's say total current will be I1 plus I2 plus I3 plus I4, and accordingly the voltage generated at the output will be this current I multiplied by R1. So the output voltage will be given by minus times, because the current is flowing out of this 0 volt impedance, this is coming here, so the output will be negative, minus times R1 into I1 plus I2 plus I3 plus I4, which is V1 upon R2 plus V2 upon R3 plus V3 upon R4 plus V4 upon R5. So we have just simply written voltage as resistance multiplied by the current, which is the sum of these individual currents. If we put in this circuit R1, R2, R3, R4, R5 as same, so if R1 is equal to R2 is equal to R3 is equal to R4 and equal to R5, the equation look something like this. We have minus, which is outside, and then V1 plus V2 plus V3 plus V4. So which is nothing but the sum of all the voltages or all the signals coming in to this summing amplifier, and the output is nothing but the simple sum, algebraic sum of all the voltages. There is a negative sign, so that is not an issue. We can put again a inverting amplifier after it to change the polarity. This is simple algebraic sum. However, if we want the weighted sum, for example V1 plus 2V2 we want, then in that case we can put R3 as half of R1. So this will become V1 plus 2V2 here, because R1 will be twice of R3. So in that way we can also produce the weighted sum as well by this summing amplifier. So this is very important circuit, very widely used circuit in the laboratories and many other places. We have multiple signals coming in, we want to have the sum of all the signals. So now let's go to the software and design systematically how do we start in KiCad using this OpAmp, which is a general purpose OpAmp. So let's go to the software. So when we go to the software, we create a new project. When we give it the project any name, these two files will appear in this project files dialog box. This is the schematic file and this is the PCB file. So first we go to the schematic editor and start designing the schematic what we just saw in the last slide. We go to this schematic editor. This is how the window will look like. Now we want to place our components. So we go to the left, go to this right toolbar and click on the add symbol. So this will load all the symbols and footprint libraries once we are invoking it, and the dialog box will come something like this. Now we need to add the OpAmp first. So we write OpAmp, which is general purpose OpAmp. Now there are many OpAmps available here in this library file. For example, LM741 OpAmp is very widely used OpAmp. Let's try for that first. LM741 OpAmp. So this is the OpAmp which is manufactured by Texas Instruments. Here if we see on this below dialog box, we have a short description of this component, which is operation amplifier, and data sheet is available here at this link. However, if we see, we have the symbol available in KiCad, which is this symbol for LM741. However, there is no footprint specified. So there is no default footprint available for this particular component. So there are two options now. One is we design the footprint for this as well, this OpAmp, or we download from TI Spice from the Texas Instruments manufacturer's library. For this example, let's take the another OpAmp because the footprint is not available here and we need not to create the footprint for all these ICs. These are general purpose ICs. These are available from many manufacturers. So we look around for any other manufacturer who is providing this OpAmp and the footprint is also available. So we will not go for this component. We go to another component. Let's write the general purpose OpAmp. So it is suggesting that we have one general purpose OpAmp. This is LMV601 and we see the symbol is available as well as the footprint is also available. We see in this window there is a footprint associated with this OpAmp. So we can use this operational amplifier. To know about this amplifier, there is a short description available here, which is a 1 megahertz low power op amp, which is general purpose op amp. 2.7 volt is the voltage. However, if we want to go to detailed specification, we have the data link available here. We can simply click on it and get the data sheet for this particular amplifier. So when you click on that link for data sheet, this will open up the data sheet from the manufacturer. So the manufacturer is Texas Instruments, and these are the detailed specification of the component. Typical supply voltage is 2.7 volt and supply current is 100 microamps. Gain bandwidth product is 1 megahertz and so on. If we go below, then we have other detailed specification of its pin description. For example, this is the top view of the package, and we have this pin number 1 which is input positive, pin number 3 which is input negative, pin number 2 is ground, pin number 6 is the positive voltage here, pin number 5 is shutdown signal, 4 is the output. So this is the pin functions for LMV601. As per the pin number, this is the name for that particular pin, whether it is an input or an output. So there are multiple ICs available. LMV602 has 2 op-amps inside it. However, we are using only one op-amp, so we will use the IC which has only one op-amp inside. These are the absolute maximum ratings of this component. The supply voltage maximum is the 6 volt. We cannot apply more than 6 volt of power supply or signal across this component. Typical voltage is given 2.7 volt, and these are other specifications. So whatever is required for our application, we need to see in this data sheet. We want to see the footprints in this data sheet. Though we already have footprint in the KiCad software, still we want to see how the information is given in the data sheet. So we go to the very end, and generally the footprint information is given at the very end. So this, for example, is the package, and these are the dimensions given. So all the dimensions, for example, this is the width and this is the length of this package. These are the pin lengths, the dimension of these pins, the thickness, the height of this complete package. All these information are already available in the data sheet. So based on this, we know that output geometry of the package, we can create the complete PC, the footprint of this device. So it's already available, so we need not to create it. But if not available for any particular component, we can always search for the data sheet and look at the very last of the data sheet for the footprint information. These are the footprint information. The same thing we need to have in the KiCad software. So this is how this specification sheet or the document, the data sheet look like. We need to pick our component based on the data sheet which is suitable for us. The very important parameter for choosing all these components is the supply voltage. So once you fix your supply voltage, you need to pick only those components which support that supply voltage. So no component should be underdriven or overdriven at that particular particular voltage. If we decide, let's say we want to go for the 5 volt supply voltage, no component should be selected for which the maximum rating is lesser than 5 volt. So all components should have the electrical maximum power rating which is higher than 5 volt. So this is how we choose the component primarily. Rest depends on the functionality, so that depends on the application. So this is the data sheet, and now we see that this op-amp is suitable for our work. We close this data sheet, go back to this choose symbol dialog box, and we want to go with this operation amplifier. So we choose this and click on OK. This component will be available here in our schematic window. So we click on it and then press escape. So this symbol is now available to us. We can make the schematic using it. Now the very first thing we should do is put the supply and ground connection, because all these components, all these circuits need to be having some voltage source to operate. So let's put the ground and VCC. So we go to this symbol, this is add power, we click on it, we write G and D, which is the ground connection, click on it, and then we place it here, press escape. This is the ground connection. Similarly, we put the VCC, so we write VCC here, and we put the VCC on top, and then press escape to come back to the click view. Now we need to connect these ground and VCC to this symbol. We choose wire here, click on add wire, and this pin 6, which is V positive or the positive power supply, we click on it, route the wire up to VCC, click on the other end, and the wire will snap to that particular terminal. Then we take wire again and connect the ground pin to the pin 2 of the symbol. This pin 5 also need to be connected to ground because this is low enable signal, so we need to provide a low voltage at this terminal as well. So this we can see in the data sheet. Some components come with the low operating voltage. When we apply low, then they work. Some component come when we apply high, so that we need to check carefully in the data sheet. So now we have our op-amp here, and the power supply is connected here. Next we bring other components. So if we see in the schematic, we need 5 resistances, 1 in the feedback and 4 in the input. We have 4 inputs, so 4 resistance we need. So we again click on this add symbol. This will open up this window again. We write R for resistor, and this resistance symbol will open up. We click on it. We see here now this is a general resistor symbol which is shown on the right. There is still no footprint specified here. So for this particular resistance, we just want to use the symbol for time being to create the schematic. When we will go for the PCB design, that time we can specify the type of footprint we want to have for that particular symbol. So we choose this general purpose resistance specified by R. We click on it. This comes up here. We can use mouse middle wheel to zoom in, zoom out on the schematic. Now this resistance is in the vertical direction. We can press R to rotate it. So if we press R, this will be rotated here. So this is our feedback resistance, for example. Now we want to have 4 more resistances for the signals. So we put one more time, we click on it, the again 2 symbol will open up, we press on OK, press R, this is the R2. Again we press anywhere in the schematic, the same dialog box will open automatically. We again choose R, click on R, we press rotate to rotate it. This is second resistance, we again click on it. This is third resistance, and let's go for one more. So now we have these 4 resistances. These 4 resistances are used for input signals which are 4 V1, V2, V3, V4 we want to receive through these resistances. Apart from this, we need to have some connection on the PCB where that signal will land on the PCB. For that we use something called jumper wires or the connection. So we can import that also using this add symbol dialog box. We click on it, we type con, which is short for connector. So for this, first we want a connector which is the 5-pin connector. So we can go for this con, this is 01 cross 05. It means it has one array of 5 pins. So we can go for it because we have 4 inputs and 1 output to go outside the board. So total 5 signals we want to deal. So we can go for 01 cross 05, which is one array. This is one array of 5 pins, 1, 2, 3, 4, 5. So this is one array of 5 pins. We want to choose this connector to be used in our schematic for our signal input and output. So this is our connector for the signals. Similarly, we are using 2 supplies. One is the VCC, which is the positive supply, and GND, which is our negative supply. This also need to be provided from outside. So there should be some landing pad on the PCB where we want to provide a positive voltage and negative voltage from outside the board. So we use one more jumper wire or connector to provide the supply voltage. So we again go back to add symbol, and this time we want only 2 pins, one for GND and one for VCC. So we go for con 01 cross 02, which is one array of 2 pins. So there are 2 pins, 1 and 2, one we can use for VCC and 2 we can use for the ground connection. We click on OK, and this connector will come here. Then we press escape. Now we have all the symbols, all the components imported to schematic editor. Next, we need to now connect all these components together as per our circuit diagram. So in the circuit diagram, first we route the power and supply, power and ground connection. So we click on this add wire, and pin 2 is our ground connection. Pin 1 is our VCC. So we go here and connect it to VCC. So wherever the wire is connected, you can see this green dot here. It means this wire is connected to this wire, which is going from this component to VCC. So this is a connection, and this jumper wire or the connector is used to supply the voltage here, which will go to this point. Next, we have these feedback resistance which need to be connected to the terminal V negative, the negative point of OpAmp. So we click on this and we connect this feedback resistance, and on the other side this feedback resistance is connected to the output. So now our feedback resistance, which is R1 here, is connected at the output. The positive terminal of OpAmp should be grounded as per the diagram. So we click on one and connect it to ground. So here we see this dot has appeared on this wire. So this wire is connected to ground. However, this is crossing over this horizontal wire as well, but the dot is not there, it means they are not connected. So if dot happens here, then only the wires are connected, otherwise they can route on top of each other. This is just for our visual representation that wires are going from here and there, but they are not connected. Next we need to prepare the signal ladder. So this is how they need to be connected. All these resistances are connected to this node, and this node is going to the negative terminal of OpAmp. So this is the negative terminal. So all these resistance are connected to this. To apply the signal, all these pins are connected to these resistances. So for example, this pin 5 goes to this R5, this pin 4 go to this R4, pin 3 go to this R3, and then this pin 2 go to this R2. And the remaining pin 1, which we will use for sending the output, so this pin will be connected to the output. So we can zoom in and zoom out as per our comfort and connect it here. So now if we see the close schematic, this is how our schematic look like. All these pins are connected as per our schematic diagram, and the circuit is ready for going to PCB. However, before going to PCB, we need to assign the footprint, because the OpAmp we used, which is LMV601, for which the footprint was available, but the resistances what we used and these connectors what we used, there is no landing pattern available in the software, which is by default footprint which software can take. So we need to assign some already existing footprints to these elements, these components, whatever we are using. So we go to the footprint assignment tool. So there is a small button here which says assign footprint. We click on it and this will open up all the symbols whatever we are using in our schematic. So these are the symbols we are using in our schematic. On the left side we have these footprint libraries. These are all the libraries available in the software, and in that particular library, for example, we can take any library here. These are all the footprints available on the right side. So we can choose any of the library and we can see what are all the footprints available inside that library. We need to assign now the footprint to each and every symbol. If we see at the line 8, which is U1, this is our LMV601 and we see there is already an entry there. So this says that the footprint is already assigned to this element only. However, for the other elements, the footprint is still not assigned. So we need to assign this one by one. So these are the connector pins. So we click on this J1, which is connector 01 cross 05. So this is a 5-pin connector. For this, we can go to the connector libraries and we have something called T connectivity library here. And here if we see, we have so many footprints available. We can go for 1 cross 05 any connector. So for example, this is 1 cross 05. So 1 by 05 means the one array of 5 pins. This is the PCB footprint we can choose for this particular connector. We click on this and we double click. This will be assigned automatically to our 5-pin jumper wire. Now similarly for the 2-pin, we want to assign a footprint. So we again be in the same T connectivity library and we go to the 1 cross 02, so which is here. We can enlarge it. So this is 1 cross 02. One is the vertical and one is the horizontal one. So we can choose any one of it. So we, for example, use vertical. So we go for the vertical one. And click on, double click on it. This will be assigned to this. Now we have resistances. So we need to assign footprint to resistances now. We go to the footprint libraries here and select the resistor. So there are two types of libraries available. One is the SMD, which is surface mount device, and THT, which is the through hole devices. So we go for the through hole device, let's say, and then in this through hole we can choose any of these footprints. So for example, we can go for different types of resistances just to show that we can use different type of resistance for different type of applications. So for example, we are using, for this resistance we are using this, for other resistance we are using this. Just randomly we are taking. However, you need to check your component for that particular footprint and you can choose that only. For here, to show that how different resistance look in the PCB, we are choosing different resistances. So now if we see in this symbol footprint assignment dialog box, all the symbols here, they are assigned a particular footprint here. All have associated footprint. Now we click on OK. We save our schematic, and the next point is to run the electrical rule check, which is to know that if we are violating any electrical rule or not. So this is the electrical rule checker. We click on it and run ERC. It will run all standard electrical rules which are inbuilt in the software. So if we run ERC, we are ending up with two errors, which is input power pin not driven by any output power pin. So this power pin is there. This is not connected to any voltage supply. This is what the error is, and the other error is same for the ground connection. So, KiCad is telling us that these two pins are not provided any power from the other component, which is true because in this schematic we are not using any battery on the PCB. All the power we will be feeding from the outside, which is still not available in the schematic. So, KiCad is telling us that these power pins are not driven by power ports. So, this error is acceptable to us because we know that we are not using any power source like battery or so on the schematic. So, we can still go ahead with these errors. So, all the time when electrical rule checks gives you error or warning, you need to decide what you have done in the schematic, and based on that you can neglect some of the errors and warnings, or if it is a genuine error you have to correct the schematic for that particular error. So, in this case we can skip these errors because we have not used any power supply on the schematic. So, we click on close. There is no error apart from these two errors, so we can continue with the PCB design. So, we click on save and go to the PCB editor window. So, this is the switch to PCB editor. We click on this and the PCB editor window will open. In this we want to import our schematic, whatever we have prepared. So, all the components we want to import here from that. So, there is a import button where we can import all these components directly. So, this is the button available here which says update PCB from schematic. So, every time we click on this button, the software will check for the schematic and see if all the components are available in the PCB. So, we click on this thing and this dialog box will open. It says that there are multiple components available in the schematic. If we click on update PCB and close, all these components are now available with our mouse. We can click in between somewhere and this will be placed. Wherever we want we can place these components, and we click on escape. Now all these components are available in the PCB window. We can zoom to objects. This is how all the component footprint look like. Now we can go for arranging all these components, because this is the random arrangement by the software. So, we can arrange it properly so it look easy to route all these components. So, we click on the PC on the footprint and we can move it. We can press rotate to rotate it. So, this is how we can rotate the footprint. This is our 5-pin jumper wires. These are 2-pin jumper wires. These we can rotate again to put one side. So, one side of the PCB we want to put all these input and output connections. Next we have these. This is our OpAmp IC. This we can keep here somewhere, and all these resistances. This is our R2, this is our R3, this is R4 and R5. So, these are the resistances. So, you notice that these footprints are different for R2, R3, which we did purposely to show that we can use different type of components for different application For example, one path is less on power, so we can use a small resistance. However, one path is carrying high power, so that case we can use a big footprint component to sustain that power. So we choose different footprints. This is our R1, which is our feedback resistance, which is placed here. So this is our simplified placements. Now we need to use the routing to connect all these red nests. So all these blue lines, the thin lines, this says that this connection need to be made from this point to this point, this point to this point. All these connections need to be made using copper traces. This is just a symbolic representation that this connection need to be made. There is still no connection from this connector to this resistance. This is just a symbolic representation. To route the wire, we go to this route tracks option, click on it, and then start routing these traces. So we zoom on this, click on this pad, this will start this wire. And wherever it is terminating, it will auto snap on that. We go to that terminal, click on it, and that red nest will disappear and the copper wire is routed from this point to this point. Similarly, we can route this power supply from this point to this point. This is routed. We need to route all these traces. So pin 5 should be connected to this pin 4 should be connected to this R4, this should be this, and this should be this. So here we are not very optimizing the layout, we are just drawing to connect this. Otherwise this kind of bending in the traces is not advisable, though it's a power port which is providing ground from here to here, but for the signal it is highly undesirable to have these sharp bends. So we need to take care when we design for the high speed PCBs. However, this is a very low speed PCB and this should be okay. These connections also need to be made. So these are the connections for R2, R3, R4, R5, and this need to be connected to the R1. This connection need to be made from here. So now we need to make a connection from this point to this point. However, if we draw like this, then it's a very kind of trace has so many bends. So instead we can go all the way to this side, we can come back here and connect here. For this we connect here, is, and see if we still have one connection, which is this output. This need to be routed, so we go here, click here. So this is the complete PCB where we have routed all the rat nests. We have not optimized this PCB till now. This is just for the representation that this is how we connect all these components. So once all these components are connected, we can save the PCB and run the design rule check. For that we have this button, which is design rule checker. We click on this. This open up this dialog box, and if we run DRC, this is going to check up all the standard checks on our PCB. We run this DRC and we end up with one error, which is malfunctioned outline, no edge found on the edge cuts layer. This edge cut layer is which tells the software that what is the standard size of my PCB. So to do that, I need to specify the boundary of PCB what need to be fabricated. For that I go to the edge cut layer and take the draw a line to draw the outline or the boundary of our PCB. So I start from here and draw the boundary to our PCB. So this is the complete PCB with the boundary. Wherever we alter anything in the PCB, is advisable to run design rule checker. So once we are ready with the PCB, we can have a visual look at the PCB, how it will look like when it is manufactured using this 3D viewer. If we click on 3D viewer, this will open up the PCB, how it look like when we will manufacture it and place all the components together. So this is our OpAmp IC. These are all the resistances. This is R1, which is the feedback resistance. These are R2, R3, R4, R5. These are the signal resistances. These are the pins where we will connect V1, V2, V3, V4, and output will be taken at this pin 1. Similarly, the power supply to this PCB will be provided by this GND connection here and supply at this square pad. So this is how the final PCB is going to look like when we fabricate using some manufacturer assembly. So once we make it, then the step is we export the fabrication output files. So we go to File, Fabrication Output, and generate the Gerber. Here we can write the name, example, any name you can give, example file 3, and we also need to generate drill files. So we click on drill files, generate drill files, and plot. So this is going to plot all the Gerber files in this directory. You can copy these files and send it for the fabrication. So this is the complete process of making a PCB, and this is the visual representation of what we have made, which is a summing amplifier. So today we saw that we can make a analog summing amplifier right from the very scratch, where we are choosing the component which is available in marketplace with whatever is available to us which is suitable for our requirement. We use that component and import all other components whatever is needed into the schematic window. We create the schematic, we assign the footprints, if the standard footprint is not available, we choose particular footprint for our application, and then import all the schematic into PCB and route the PCB into various layers. So today we saw only on the front layer. It means the PCB is a single sided PCB because all the wirings we have done only in red color which is a front copper layer. So this is a single layer PCB which is very easy to fabricate. You can give it these Gerber files which we generated to any manufacturer. They can fabricate the PCB, ship it to you. You can purchase all these components whatever we used in the example, solder it as per this 3D viewer, and you will get your summing amplifier in the PCB. So this is all for today. Thank you.